Welcome to video number 7 for Physics 102. In this video, we do another example problem in which an object undergoes constant acceleration. You may want a copy of the problem-solving framework worksheet with you as you go through this video. Here's the problem we're going to consider. You are taking a tour of the processing facility of a major shipping company. Packages travel along a horizontal conveyor belt. At the end of the belt, the packages slide down a very slippery ramp and into the trucks. You wonder how fast the conveyor belt is moving. You estimate that the ramp is about 28 meters long, makes an angle of about 30 degrees with respect to the ground, and that the packages take about 3 seconds to make the trip down the ramp and into the truck. Following our problem-solving framework, let's begin focusing on the problem by sketching a useful picture. In this problem, we have a ramp, and the box begins its journey at the top of the ramp with some initial velocity, indicated here by a blue arrow. The ramp is 28 meters long and makes an angle of 30 degrees with respect to the ground. Now let's move on and begin describing in words what's physically going on in this problem. We know that the box hits the ramp with some initial velocity, which is parallel to the ramp in this case, and that the force of gravity from the Earth is pulling on the box straight down towards the center of the Earth. As a consequence, there must be some normal force on the box from the ramp, which keeps the box from just falling straight through the ramp. Now that we've described in words what's going on, let's begin focusing on the approximations and constraints in the problem. Well, the first one is one you might not have thought of. The box must remain on the ramp. It doesn't fly through the air. It slides down the ramp. The problem says that the ramp is very, very slippery. So we're going to assume that it's exactly frictionless. In other words, any friction in the problem is so small that we can just ignore it in this case. The box, the ramp, all of this is near the surface of the Earth, so we can just treat the weight of the box as mg. We don't need the full gmm over r squared for this problem. That would be overkill. Finally, we're going to assume that the initial velocity of the box at the top of the ramp is the same as the speed of the conveyor belt. This last constraint will help us precisely state the question in terms of things we can calculate. We can calculate the speed of the box at the top of the ramp, and since this is the same as the speed of the conveyor belt, which we're interested in, all we need to calculate is the initial speed of the box at the top of the ramp. Now that we've focused on the problem, described in words what's going on, and determined what we're going to calculate, let's start describing the physics by adding to our diagram. The first thing to add is our vectors in this case. Well, we've already added a vector to our diagram, the initial velocity of the box, which I've indicated by a blue arrow. Now I'm going to go and add coordinate system to my diagram. Hopefully you've already seen video number 6, which emphasized the arbitrary nature of coordinate systems. In this particular case, I'm going to choose the positive x-axis to go down the ramp. This might be different than coordinate systems you've seen before, but coordinate systems are completely arbitrary, as emphasized in the last video. So I'm going to pick the x-axis to go down the ramp, and I'm going to pick that because that's the direction of the ramp, and that's the direction of my initial velocity. So now my coordinate system matches the properties of the problem. The x and the y-axes have to be perpendicular to each other, so I'm going to make the y-axis come off perpendicular to the ramp. Now that I have a coordinate system, I can start defining symbols for the various items in my problem. One thing conspicuously missing from our problem statement is the mass of the box. Well, that's okay. I'm just going to slap a letter on it, m, for mass. We can also label the angle that the ramp makes with the ground. We're going to call it theta, as Greek letters are traditionally used for angles. The next thing we know is we know something about the time. So I'm going to define the initial time of the box at the top of the ramp to be 0 seconds. I can pick anything I want. I'm just going to pick that the box is at the top of the ramp at t equals 0. That's what this 3-line symbol means. It means define. It means that's my choice. If that's my choice for the initial time, then the final time when the box is at the bottom of the ramp is 3 seconds, because we know it takes 3 seconds for the box to make the trip down the ramp. Similarly, I'm going to define the initial position of the box at the top of the ramp to be x equals 0. Again, we see this 3-line symbol, meaning that's my choice. That's my definition. if that's my definition of x equals 0, the final position of the box at the bottom of the ramp is going to be 28 meters. We also should add some symbols to our initial velocity. So here I've called my initial velocity v sub 0, which is also often pronounced v naught, and I've given a little arrow over the symbol to remind myself that it's a vector. Now I chose my coordinate system in such a way that the velocity is only in the x direction. That was part of the motivation for my choice. So in this coordinate system, the initial velocity vector only has an x component, so I can write it v naught x hat plus 0 y hat. Now that I've given symbols to everything, the next thing to tackle is probably drawing a free body diagram for the box. We always begin our free body diagrams with a dot. In this case, the dot represents the box. Now, there is of course a force of weight on the box from the earth pointing straight down, and from our constraints we know we're going to treat weight as mg. And also from our description of the problem, we know there's a normal force pointing perpendicular to the surface of the box. Now we can see another convenient aspect of this particular coordinate system. The normal force in this coordinate system only has a y component. It doesn't have an x component. The weight, on the other hand, has both y and x components in this coordinate system. There's a component of the weight parallel to the surface of the ramp, which is the x component, and there's a component of the weight perpendicular to the ramp, which is the y component. We've discussed how this angle here must also be 30 degrees. With that information, we can determine that the y component of the weight is negative mg cosine theta. The negative sign is because the weight points into the ramp, which is in the negative y direction. Similarly, we can determine that the x component is mg sine theta. So now we've got a free body diagram and a whole bunch of symbols. The next step is to start trying to describe the physics by listing those equations that might be relevant to what we have going on. Well, the box's mass isn't changing. So Newton's second law with constant mass, the sum of the forces equals ma, written as a vector, must be true. Now, vector equations are tough to deal with, so we do what we'll normally do and split this vector equation into two equations. One for the x components of the force, one for the y component of the force. Newton's second law in vector form must be true component by component. So the sum of the forces in the x direction has to equal the mass times the acceleration in the x direction. Similarly, the sum of the forces in the y direction is going to be the mass times the acceleration in y. In this particular case, we know the box can't leave the ramp, and so the acceleration in the y direction has to be identically 0. It's not moving in the y direction. The y direction is perpendicular to our ramp, and the box doesn't leave our ramp. So there's no change in the y position, so there's no velocity in the y direction, so there's no acceleration in the y direction. Also, we can look at our free body diagram for the y direction. We see that there are two forces, a normal force and a y component of the weight force. Putting these two together and combining that we know the y component of the weight force is minus mg cosine theta, we get the sum of the forces in the y has to be the normal force minus mg cosine theta. What else do we know? We know that the ramp is frictionless. This is another one of our constraints. This means that the only force in the x direction is the x component of the weight. So substituting this into our Newton's second law for the x direction, and using that we know the x component of the weight is mg sine theta, we get mg sine theta equals max. The masses in this particular expression cancel out. Now we can also see that the acceleration a sub x is a constant. It's g sine theta, 9.8 times the sine of 30 degrees. That's a number. Since the acceleration in the x direction is constant, we can use our kinematic equations. We have some information about a sub x. We also have some information about the change in displacement. We have some information with regards to the time, and we're interested in the velocity in the x direction initially, so this kinematic equation is probably the correct one to use. Now let's start planning a solution by making a rough estimate of our result. I honestly have no idea what a good value for the speed of a conveyor belt should be. But more than 100 meters per second seems really fast. So if I get a number bigger than that, I'm going to start questioning my logic. So now let's begin planning a solution using the equations we have. Thinking about the y direction, we have Newton's second law for the y direction. We know that the acceleration in the y direction is equal to 0. And from our free body diagram, we know that the sum of the forces in the y direction is the normal force minus mg cosine theta. For the x direction, we've worked out that mg sine theta is equal to the mass of the box times the acceleration in the x direction. We also have this kinematic equation, which we know applies because the acceleration in the x direction is a constant, 9.8 times the sine of 30 degrees. Since v naught x is what we're interested in, it seems reasonable to start with our kinematic equation. Now let's have a look at this. What do we know in here? We know t. T is the time it takes for the box to slide down the ramp. In this case, 3 seconds. We also know the initial position of the box. We defined it to be 0 meters. And we know the final position of the box. It's 28 meters. So we've already got everything but v naught x, which is what we're interested in, and the acceleration in the x direction. But wait, we do know the acceleration in the x direction. It's g sine theta. Notice we didn't even use any of the information in the y direction. We already have everything we need to solve for v naught x, which I'm going to leave to you to solve as part of the quiz for your video. This concludes this video.